Now concerning the standing waves. Students are supposed to watch the videos about standing waves before attending the online session. So as you can see, some links are pasted on the screen here, and you can find it in the description box of the video, this video. Now, what are standing waves? A standing wave is a wave pattern that results when two waves of the same frequency, wavelength, and amplitude travel in opposite directions and interfere along a medium with fixed boundaries. The node is a point in a standing wave that maintains zero displacement. The antinode is a point in a standing wave halfway between two nodes at which the largest displacement occurs. Case 1. This is one case. A string is being vibrated by a vibratory source, producing a periodic wave along it, and only one loop is formed. The loop is showing the crest of the incident wave and the trough of the reflected wave. The number of nodes are two. The nodes are those that maintain zero displacement, which are this boundary and the other one here. And the number of antinodes, we said by definition, is halfway between the nodes. So here it's 1. Now in case 2, there are two loops formed. Again, one loop consists of a crest of the incident wave, for example, and the trough of the reflected wave. So how many nodes are there? 1, 2, 3. These 3 points, the particles of the medium do not displace neither upwards nor downwards theoretically. So these are 3 nodes, and the number of antinodes is 1, 2. So 2 antinodes. Case 3, as you can see, as the frequency increases, in this case when we move from case 1 to case 2 to case 3, we are increasing the frequency of vibration. Thus the frequency of the periodic wave increases. And as the wave propagates through the same medium, we said in the first lesson, if the wave propagates in the same medium, it keeps the same speed. Now if the frequency is changed according to the formula V equal lambda times f, if V is constant, as the frequency increases, the lambda decreases. So as you can see here, going from case 1 to case 2 to case 3 and to case 4 and so on, increasing the frequency, the wavelength is decreasing. So in case 1, this represents half a wavelength. In case 2 now, a whole wavelength is shown. In case 3, one wavelength and a half. We are going to discuss this in details in the next slide. So now for the nodes and the antinodes, in case 3, when there are 3 loops, the order is 3. 1, 2, 3, 4 nodes and antinodes 1, 2, 3. Finally, case 4, in which there are 4 loops formed. The number of nodes are 1, 2, 3, 4, 5. 5 nodes, and the antinodes 1, 2, 3, 4. As you can see, you should notice that the number of antinodes is always less than the number of nodes by 1. Now the condition for standing wave to take place. Case 1, case 2, case 3, and case 4. In case 1, now we want to find the relation between the length of the string. In order to find the condition, we need to find the relation between the length of the string or the rope through which the wave propagates and the wavelength of the wave. So in this case, as I said before, this represents half a wave. So here lambda over 2 is equal to the whole length of the string. In case 2, this is a crest and a trough, so the distance here is a wavelength. Wavelength equals L. It's equal to the whole string length of the string. Case 3, now we have crest, trough, and crest. So this is a whole cycle here, and this is half a cycle. So distance-wise, this is lambda and a half. So it's 3 lambda over 2 equal to the total length of the string. And finally, for case 4, this is one cycle and this is another cycle. So we study, like we only choose either the incident wave or the reflected wave to be able to determine whether there is one cycle, 2 cycles, and so on. So here, considering the incident wave, which is this one here that I'm tracing, okay, So this one has crest trough. This is one cycle, crest trough, another cycle. So this is 2 lambda equal to the length. Now you should notice that every time as the frequency increases, the difference between one order and another is that the lambda is increasing by half. We have half lambda, lambda, lambda and a half, 2 lambda. Okay, so only certain frequencies produce standing waves on a fixed string. And in other words, only if the wavelength of the traveling waves satisfy the following condition, a standing wave occurs. The condition is that n lambda over 2 equals L. Then we can do some mathematical work and find that lambda, or express it as lambda equal to L over n, where n is a positive integer here, which means a natural number. So n is 1, 2, 3, 4. So if n equal 1, then there is only one loop. If n equal 2, 2 loops, n equal 3, 3 loops, n equal 4, 4 loops, and there are higher orders of standing waves of oscillation. Now, as a direct application about the previously discussed ideas, watch the next video.